Okay, so we're going to review Unit 1 now. We're doing just a basic overview of what we learned from Unit 1. Remember, Unit 1 was about graphs, mean, median, and mode. We're focusing on the graphs and a few other things with this PowerPoint. So the first type of graph is categorical graphs. Remember, categorical variable is something like favorite color or zip code, where you don't take the average of it, or it wouldn't make sense to take average. So typically something that's a category, but also a few numbers that are identification numbers like zip code, where the number itself doesn't really mean anything. You can't do a lot with categorical graphs. So what you discuss when you look at the graph is the most popular, the least popular, and anything else that you think is significant. So there's not a lot to talk about. Probably won't be describing one on the AP test, but just in case, I'm reminding you what it is. For bar graphs, remember the bars do not touch. That's how we differentiate between a bar graph and a histogram. So bar graphs are for categorical and the bars do not touch. Make sure you have a title, make sure you have your x-axis labeled, so that should be fruit type. And then your y-axis labeled as well, that would be frequency or relative frequency. In this case, frequency is number of people. You don't have to be fancy and color coordinated. This is just for fun. They're even the same color that those fruits typically come in. So if I were describing it, I would say the most popular choice for nicest fruit is blueberry. The least popular choice for nicest fruit is grapes. Then we have a pie graph. Make sure you put a title. Make sure you label each section and put either the amount or the percent. This graph put both. I like to put the percentage, but you probably won't make one on the AP test. But just in case, looks like that. You can have a key if you need to, but we don't need a key if it's big enough. We can just label the sections themselves, which is easier. Then we also have numerical graphs. Remember, there are two types of numerical variables. There are discrete variables, which are counts of something, or continuous variables, which are measurements of something. So counts of something, how many writing utensils you have in your bag, that would be a count. Measurements of something, how tall you are, how much time it takes you to complete the PowerPoint or the homework, whatever, anything like that. So measurements, they typically can be, or they can be decimals. You can go out as many numbers after the decimal as you choose. Discrete, you're counting, it's only certain values that you can have. To describe, remember to write in complete sentences and use context throughout the description. And don't forget your socks. So for socks, we have our shape, which can be normal, skewed left, skewed right, uniform, bimodal, symmetrical, etc. Those are the main shapes we learned about, but there might be other shapes out there. Talk about your outliers, your center, which is the mean or the median. You don't need both, one or the other is fine. And the spread, which is the range or the IQR or the standard deviation. For most graphs, we'll do the range. Box plot, you can pick IQR or range. I don't do the standard deviation unless they specifically give it to me because that one's more work. And then context throughout the whole description. So it's not one sentence. That should really be in every sentence. You're including units, the title of the graph, what the data actually represents. The other thing is comparing numerical graphs. You still use socks. You're going to state the shape and outlier for both, but you need to make sure you compare the center and spread. So that means you have to give approximate values and say which one is the highest. It should be obvious that 5 is greater than 3, but you have to explicitly say it in your description. There are several types of numerical graphs. The first is a histogram. We have histograms for discrete data and also for continuous data. Remember, the bars do touch for both of these. For discrete data, this is counting, such as counting the number of children in a family. The bars are centered over the number. So we're centered over the number 1 for all the families with 1, and the bars touch in between. Make sure you label both axes and include a title. For a continuous bar graph, you put the lines going between the points. So it looks like there are about 3 or 4 trees that have a height between 100 and 150 centimeters. And then there's about 30 trees that have a height between 150 and 200, and so on. Make sure, again, you label both axes, you include a title. When you describe this graph, remember the range goes from either 100 to 350 is the most it can be, so the highest the range can be is 250. The lowest would be from 150 to 300, so the lowest possible range is 150. We don't know the exact range without the original data, so we would give an interval for possible range values. Same thing with the median on that problem. A dot plot, we can use discrete or continuous data for a dot plot. We use X's or dots, but we have to make sure they're distinct. So here I use dots. If you do X's, make sure they're the same size with the same spacing, just like I did with the dots. You label the X-axis, you also have a title. For a stem plot, this is where you have the stem with the first digit and then the other digits going after. So in this case, my stem represents my tens place, and the leaves, because this is also called the stem and leaf plot, represent the ones place. So those can represent any place values you want. You can have 3-digit numbers, and you can be putting 2 digits over here, whatever is appropriate for your specific data set. Remember, even if there are no numbers on that stem, if it's between other stems, you have to put it. So even though there was nothing with the 2, I can't skip 2 because I need to know that there's a gap between 18 and 33. This key could also represent, say, 0.10. So it could be the 10th place and the 100th place, or it could be 10, so it could be 100. So you could always be adding a 0 to the end, or 0.010. There's lots of different ways it can be read, so it's really important that you have a key. In this case, they're saying 1/0 represents 10, but it could represent any place values you want. And again, make sure you have a title anytime you make any kind of graph. Yep, here it is again. Do not forget titles or labels. That's a silly thing to lose points for. Let's go into a little more detail for the shapes. For a symmetrical distribution, the mean and median are approximately equal. Well, if it's a perfect symmetrical distribution, they would be definitely equal, but typically it's approximate. So mean and median should be about the same. A uniform distribution, remember, is a straight across where everything has an equal chance. So it should be, or an approximately equal chance, it should kind of look like a rectangle. And this one is symmetrical as well, as is a normal curve. Remember, a normal curve is a bell-shaped curve, which is approximately symmetrical. If you can be more specific than symmetrical, you should, but normal and uniform, by saying normal or uniform, but sometimes you can't. Sometimes you just have symmetrical. Bimodal is a graph with 2 maximums, so there needs to be a distinct dip between the data like this. And then there'd have to be multiple data on both sides. We can't just have like 1 or 2 on one side and 100 on the other side. If there's 1 or 2 and 100, the 1 or 2 are just outliers. It's not another mode or max in the data. And this might or might not be symmetrical. It's not a symmetrical distribution specifically, but sometimes it is by chance. Then we have skewed left and skewed right. Remember, skewed left is the same thing as a negative skew, and skewed right is the same thing as a positive skew. The skewed side is the side with the longer tail or the side with the outliers. So in this case, the longer tail or the outliers are on the left side. In this case, they're on the right side. Because of those outliers or just extreme values, the mean is pulled in the direction of the skew. So in a skewed left distribution, the mean is less than the median. In a skewed right distribution, the mean is greater than the median. So the mean is pulled towards the skew. Median is not affected by the skew of the graph. These are obviously not symmetrical. By very definition, a left skewed or right skewed cannot be symmetrical. Now this graph, remember, is a cumulative relative frequency plot, or relative cumulative frequency plot, or ogives is also what they're called. I have never seen them on the AP exam where you have to make one. They've had similar problems where you might be asked questions about it. You probably will not be making this graph. You probably won't see any questions this year since the exam's much shorter, and this is I've only seen something like this a couple of times. But we'll still talk about what this graph means. You could see it in the future. And if by chance it shows up on the AP exam, hopefully something sunk in. So what this graph represents is we have the total percent up to that point. So there were 2 presidents who had an inauguration age between 40 and 44, which represents 4.7% of all of the presidents up to the point where this graph had been made. So you increase by 4.7%. There are 6 presidents who were inaugurated between 45 and 49. So this graph goes up. 6 people represents 14%, so it goes up 14%. And then we go up by this amount every time. So this is the frequency. This is the relative frequency, or the proportion. That's how much we're going to go up by. This is the cumulative frequency. So it's the total amount up to that point. This is the relative cumulative, or cumulative relative, whichever you prefer. This is the percentage adding up everything to that point. So the cumulative relative, because it's a proportion, frequency. So obviously we should end at 100, because at that point 100% of the data has happened, because 100% at this point in time of presidents were inaugurated before the age of 70. So you can see how much we went up by each time. And then the reason this is helpful is because, remember, a percentile is the percent below that point. Since we created this graph, we can now find percentiles, which is the main advantage of a graph like this. So you might be asked questions like, if Bill Clinton was at the 10th percentile for his age at inauguration, what was his age at inauguration? So 10th percentile means 10% of all presidents were younger than Bill Clinton when they were inaugurated, which is obviously not a lot. That means he had a younger age than most presidents. So right here we can see, if we go to the 10th percentile, what we're going to do is we're going to start, we're going to start from 10%, and I'm going to try to draw a straight line on this tablet. It's not even a little bit straight. It's really hard on a tablet, okay? Looks like it's about 47. Let's see how I did. Yep, I did pretty good. It is about 47. I don't know why the answer's not here. Approximately. What percentile would a president be if he was inaugurated at age 57? So it works the other way. You can start with the age and you can figure out the percentile, or you can start with the percentile and figure out the age. So at age 57 is about here. %. Let's see. Hey, that is what I got with actual straight lines. Approximately. These are obviously approximate values. If you were drawing this on paper, I would use some sort of straight edge to try to get a straighter line. What is the median age of inauguration? So what I see a lot of people do on graphs like this is they try to go to the median of the ages here. So they go from 40 to 70. But the median is not necessarily right at the middle. Our data could be skewed more towards the left or more towards the right, which it looks like here it's probably skewed more towards the right, I think. I don't know. What is the median age of inauguration? The median is where you have 50% below and 50% above. So the median is another way of asking for the 50th percentile. So that means I'm going to go to 50%. And remember, those dots are right at these lines. So if I land on that dot, I should be going down to 55 for sure. And yep, that's what I got. You can see in the picture as well. Okay. So here it has actual straight lines being used, but we got the same answer even with our not perfect lines. By our, I mean mine. A few vocabulary terms from Unit 1 about central tendency and variability. First is a parameter. A parameter is a number about the population. So for a parameter, that could be like the population mean. That would be the mean of all of the people in the population. Versus a statistic is a number about the sample. We typically don't know the parameter. We're estimating it with a statistic. So the statistic would be the sample mean that we got, whereas the parameter is the actual population mean, which we can only get the exact value for that if we survey the whole population, which is often not possible because the population is very, very large. When it's very small, then we can't do it. There are a lot of useful things if you type your data into your list and go to stat calc, one of our stats. It gives you the mean, the standard deviation, the median, Q3, Q1, a whole lot of other numbers. The next thing is the interquartile range, abbreviated IQR, which is Q3 minus Q1. Q3 is the 75th percentile, and Q1 is the 25th percentile. Variance is just standard deviation squared. It's one of the steps in calculating the standard deviation. Standard deviation is a measure of the average distance from the mean. So if we're looking at standard deviation, that's representing a way to measure the average distance from the mean. Something is resistant if it's not affected by outliers. So things that are resistant, meaning they are affected, they are not affected by outliers, are the median, the mode, and the IQR. The median is resistant because it's just the number in the middle. The numbers at the very end don't matter. The mode is resistant because that's typically going to be a number somewhere in the middle because it's something that's occurring a lot of times. If a number is occurring enough times to be the mode, then that number is probably not really an outlier. The IQR is resistant because it's the range of the middle 50% of the data. So it's Q1 minus Q3, 25% minus 75%. Any outliers would be at the ends of the data. Then for not resistant, so these are things that are affected by outliers, the mean is not resistant because if you add all of the numbers together, you're obviously adding the outliers, which is going to affect your mean. Range is max minus min. Any outliers would be the max or the min, so that would definitely be affected. Standard deviation is average distance from the mean. If a point is very far from the mean, obviously the standard deviation, the average distance from the mean is going to be higher, and therefore so is the standard deviation. Linear transformations and combinations. So measures of central tendency, such as the mean and median, are affected by addition, subtraction, multiplication, and division of a constant. So central tendency, mean, and median are affected by adding, subtracting, multiplying, or dividing by a constant, and that constant is being added to all numbers in the data set. Measures of variability, such as standard deviation, range, and IQR, are only affected by multiplication and division of a constant. The reason for that is variability is how spread out the data is. If we add the same number to every number in the data set, every number moves by the same amount, so the spread of the graph doesn't change. But when you multiply or divide every number in the data set by a constant, some things increase by more than other things, so the spread of the graph is changing. So this first rule is when you're adding or subtracting or multiplying or dividing by a constant to every number in the data set. But if you're taking two different variables and you're combining them, so this is when you have two different variables, so both things can change, you add your means or subtract your means depending on if you're adding or subtracting those data sets, and then you add the variances of the standard deviations. So sigma of a squared plus sigma of b squared will give you the new variance. This is for addition or subtraction, you always add, and then you square root it to get the standard deviation. I like to think of it as Pythagorean theoreming the standard deviations, which I don't think is supposed to be a verb, but I like to use it that way anyways. An appliance repair shop charges $30 service call to go to a home for a repair. It also charges $25 per hour for labor. From past history, the average length of calls is 1.25 hours with a standard deviation of 1/3 of an hour. Including the charge for service call, what are the mean and standard deviation for the charges for labor? So make sure, since this is measured in per hour, that we use the hours and not the minutes. So this is just some old school algebra to start with. Y would be our price, and our price is going to be a $30 fee plus $25 per hour. So Y is the price, X is the number of hours, and this is how we would individually calculate everybody's price. So for everybody's price, we'd be adding by 30, which is adding by a constant, and multiplying the number of hours by 25. Start with the multiplication and then the addition. So we're multiplying by a constant and we're also adding a constant. Remember, the mean is easy. The mean is always what you want it to be. I just plug in my overall mean. So I plug the 1.25 hours in for X, and I get $61.25. But when I do the standard deviation, remember everybody added 30, so the spread of the data did not change when you added 30. So I'm not going to add 30, but multiplying by 25, different people or spreads the data out in different ways depending on their original time. So I take the overall standard deviation time, I multiply by the constant, but I do not add 30. But then for this one, bicycles arrive at a bike shop in boxes. Before they can be sold, they must be unpacked, assembled, and tuned. So each of these are going to be variables: the time it takes to unpack, the time it takes to assemble, and the time it takes to tune. None of those are constants. All of those can change. So instead of using linear transformations, we're going to use linear combinations. What are the mean and standard deviation for the total bicycle setup times? The mean is easy. It's always easy. It's exactly what you think it should be. You add all 3 steps together to get the total mean. For the standard deviation, though, you add the variances. So I'm going to square each of these numbers, add them together. That'll give me the new variance. So then I need to take the square root of that to get my final answer. Make sure you include units on mean and standard deviation. Our next thing is box plots. So box plots are a really useful little graph. They have their advantages and disadvantages just like everything else. But it's really nice because everybody's looks the same, and it's a really good way to see the overall quartiles of the data. So when you make a box plot, you start off by making a box. The box starts at Q1 and it ends at Q3. So the length of the box is the middle 50% of the data. Remember, Q1 is the 25th percentile, Q3 is the 75th percentile. So it's the middle 50% that's called the IQR, or the interquartile range. The median is the number in the box. That might not be right in the middle. That can be anywhere in the box, just depending on where the 50th percentile is. Then I figure out what my fences are. To figure out what my fences are, I do Q1 minus 1.5 times the IQR. So Q1 minus 1.5 times the IQR, Q3 plus 1.5 times the IQR. Anything that is outside of this interval, so it's not between our 2 fences, is considered an outlier. So in this case, it looks like there was 1 outlier on the left and 2 outliers on the right. And then my whiskers, or the lines, go to the largest or smallest number that's inside of the fence. So it doesn't go to the actual fence or wall. Wall and fence are the same thing in this case. It goes to the smallest or largest number in that interval. Remember, you can make this on the calculator by typing all of the numbers into L1 and then turning the box plot on. So second stat plot, turn your box plot on, and then zoom 9. So you can do that. On the AP exam, though, I've never seen them have you make it from scratch that way, where they give you all the data. But I have seen it where they give you Q1, median, Q3. They give you some of the numbers so you can figure out if there's any outliers. And also so you can figure out what the largest and smallest value are. So they might not tell you every number in the data set, but you should still be able to make a box plot. Next thing in Unit 1 was z-scores. Z-scores are a standardized score. They represent the number of standard deviations away from the mean. That should all be 1 bullet. So how far you are above or below the mean in terms of standard deviations. It's standardized, so we can compare things from 2 completely different data sets, like SAT score and ACT score. So you can compare them based on the mean and standard deviation overall and what you actually got. So for example, Sally's taking 2 different math achievement tests with different means and standard deviations. The mean score on test A was 56 with a standard deviation of 3.5, while the mean score on test B was 65 with a standard deviation of 2.8. Sally scored a 62 on A and a 69 on B. On which test did Sally score the best? So it's not necessarily the 69. You need to compare this by calculating z-scores. So X represents your actual score minus your mean divided by, minus the overall mean divided by this overall standard deviation. Like so for both numbers. My z-score for A was definitely higher. That means Sally did better on test A because you want a higher test score. So you're going to look for the z-score that's higher. Most of the time you want the higher z-score, but there are some things where a lower z-score is better. So make sure you're paying attention. Do you want to be below the mean, or would you rather be above the mean? Next thing in Unit 1 was the empirical rule. You probably won't be solving probability questions with this specifically because we can always use the normal CDF in our calculator or inverse norm in our calculator to solve these questions. But it can be helpful to remember these percentages when you're answering other types of questions. It can also help you get an answer and then see if that answer seems reasonable or if it seems crazy. So you can figure out if you're doing it right or not. Remember, the empirical rule only applies to a normal curve. So make sure you aren't trying to use this with the skewed right, skewed left, or uniform curve. Only applies to normal. The empirical rule says that approximately 68% of the observations are within 1 standard deviation of the mean, 95% within 2, 99.7% are within 3. And that's the end. Email your teacher, come to office hours if you have any questions. I hope this was helpful in reviewing Unit 1. This is an important unit both in life, in school, and potentially on our statistics exam coming up in a month. It's a little more than a month right now.